Okay, question 8. We've got two blocks that are connected right here. And the first thing that's essential is when I consider my free body diagrams, I have to think about freeing each of these objects from each other. I want to analyze them each separately, not as connected objects, but as individual objects. If I couldn't see this and a Jedi was pulling on mass 1, what is that force going to look like? If I couldn't see this and instead it was that there was one of the X-Men over here pulling on block 2, what would that look like? So, two blocks connected by a string of negligible mass that pass over a massless pulleys that turn with negligible friction, as shown in the figure above. The mass M2 of block 2 is greater than the mass M1 of block 1. The blocks are released from rest. You already know what's going to happen, right? If this one's heavier, it's going to move this way, right? One of the things that we have to decide when we calculate problems like this is, well, even though we've got up and down, we have to decide which way is positive and negative. That'll come in the final part of this problem. The dots below represent the two blocks. Draw free body diagrams showing and labeling the forces, not components, exerted on each block. Draw the relative lengths of all vectors to reflect the relative magnitudes of all of the forces. So, the first thing I'm going to do is easy. What are the two forces that are acting up here? If I don't see this, well, gravity's pulling down on mass 1 and there's a string pulling up on mass 1. Are there any other forces? No. So I've got my force due to gravity pulling down. And before I label my tension, the force of the string pulling up, I want to think about this force of gravity and compare it over here to this force of gravity. This object's bigger, right? More mass, same acceleration due to gravity, so more force. So one of the things that you need to do on this problem is actually draw these objects vaguely, or these vectors vaguely to some sort of scale. You need to at least show that this vector is larger than that vector. Now I need to think about the tension. I want you to think about when I had two spring scales hooked together and I pulled on either end. There's some pull in either direction, but it is the same tension throughout the string. Otherwise, you could just lightly pick up one end of a tug-of-war rope and it would obliterate the team on the other side. It doesn't work that way. Throughout the entire rope, that force of the pull through that rope is the same. It means that the force of tension that this block is feeling, pulling it upward, is the same as the force that that block is feeling, pulling upward. So, when I draw my force of tension vectors here, they need to be the same length. I've even labeled them the same. Now, there's one more thing to consider here, which is when I look at this diagram, I can see that, okay, if I was going to guess which way this object would accelerate, well, I've got a larger vector moving up my page, so I'm going to assume this object's going to accelerate up my page. When I look over here at block 2, how I drew these makes it look equal. Is that an object that would accelerate? No, this looks like net force 0. So if I was going to be really, 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 really careful, I would need that force for my more massive block, force of gravity, to be a larger vector than my force of tension. I checked for two things. Did you get the right vectors on each one? So did you have these 4 vectors labeled? That was one of the points that we got. The second point was, are they vaguely to a scale as represented here? Okay, for the next part, we're going to derive the magnitude of the acceleration of block 2. Here's where a lot of mistakes were made. Block 1 is still important. It's not part of our calculation the same way you might think, but the reality is it is. So first thing I'm going to do is I'm going to think about my free body diagram that I had on the front. So I'm actually going to redraw mine right here just so that I have it to look at it. So I've got my 2 different objects. Here's where choosing some directions is important when I think about things. I know that this system is going to accelerate in the direction of the larger force. So I'm going to say that For block 2, down is the positive direction and up is the negative direction. Well, if I carry that arrow along the line here, I imagine it curving around. It's the same tension over here. Ooh, on this side, that's funny how I drew that. On this side, down means negative, unlike over here, and up is the positive direction. That arrow goes all the way around over here, pointing this direction. We're thinking about how the system is going to move since it is constrained by the string. So that's going to help me make some decisions here. So I'm going to write two equations for the net force for object 1 and for the net force of object 2. So object 1 is going to have a net force that's equal to its mass. Oh, I wrote the wrong ones in the wrong spot. Hang on just a second. Actually, you guys don't mind when I make mistakes, do you? I think you secretly love it when I make mistakes, because then it allows you to realize that I'm a human being, and when you make a mistake, it's totally okay. Oh, I can't find my whiteout. Okay. Sorry. I have to think about what's happening here. Mass 1 times the acceleration of the whole system. This whole system is going to accelerate the same because it's connected by a string. Mass 2 times the acceleration of the system, right? That's what the net force will be equal to. So the two forces that are summed together for object 1 are going to be, and here's where I have to think of my directions carefully. I've got the force of gravity acting downward, and in this case, that's the negative direction based on my diagram I drew on the other side. My force of tension is going to be up in the positive direction. For mass 2, this is going to be positive, and this will be negative. Go back and check the diagram and imagine that arrow walking all the way around to think about, does that make sense? So, object 1, the two forces added together to be equal to the net force, are going to be this unknown force of tension minus the force of gravity acting on that object. For object 2, it'll be equal to the mass of that second object times gravity minus the force of tension. I'm just listing what are my two forces added together, and I'm attending to that direction because the two objects are interacting, and I have to pay attention to that. So, the variable that I have that I can solve for here, I've got this unknown force of tension. There's no way for me to figure it out with the information I've given. So there's a couple ways to solve this problem, but here's the way I like to do it. I like to use substitution. So I'm going to solve both of these equations for force of tension. So for object 1, if I solve this equation up here, it's going to be equal to mass 1 times acceleration plus mass 1 times gravity. Work it out yourself if you need to check my algebra. For this second one, it's going to be force of tension is equal to mass 2 times gravity minus mass 2 times acceleration. So now I have two equations that are both solved for f of t. So I'm going to set them equal to one another. I'm going to change colors too, just so it's a little easier to see that I've switched to the next step of this problem. So I'm going to set these two things equal. Mass 1 times acceleration plus mass 1 times gravity is equal to mass 2 times gravity minus mass 2 times acceleration. I'm trying to solve for the acceleration of the system, right, for block 2. Well, the acceleration for block 2 is the same as block 1. That's why I'm allowed to do this. So I'm going to rearrange this so that I have all of my a's on one side. So I'm going to add m2a over here. So I've got m1a plus m2a. And I want to get all my g's on the other side. So I'm going to subtract m1g right here from the other side. m2g minus m1g. With me so far? So now I want to simplify because I've got a couple things that I'm looking for that are grouped together. So I'm going to take a out here. A is separated from mass 1 plus m2. Mass 1 plus mass 2. Those are our two masses there. So that's distributed through. And I'm going to do the same thing over here, is equal to g times mass 2 minus mass 1. So all I need to do now is remove this sum of masses from that side by dividing. So what I get is the acceleration of my system, which is the same as the acceleration for block 2, is equal to g times mass 2 minus mass 1 divided by mass 1 plus mass 2.